Alright guys, what we're going to be learning about today is a new chapter, although if you look at the title of the chapter, it's on vectors, and we already learned about scalars and vectors in chapter 2, and I mentioned that to you guys that we were going to kind of briefly touch on so that we could define the variables and the quantities that we were using in chapter 2 as variables and quantities being vectors or scalars. And so what we're going to be looking at here is I can see that we have vectors in one dimension is ultimately what we're going to be looking at in this chapter. We're going to be observing this one today. This is going to be one of the things we'll look at. When we're talking about vectors in two dimensions, that's something that we're going to kind of start getting into today, but we're just going to look at more at the trig side of it right now. So for those of you who are in pre-calc or have had pre-calc or calculus, then you understand what I'm talking about with like trigonometric identities. For those that haven't, it's okay because I'm going to be teaching it in the lesson and you'll be able to learn it from there too. The last part here, the vector resolution and addition, that's basically looking at resolution, meaning that what we're going to do is we're going to take all these vectors and we're going to break them down into smaller vectors. So that's kind of what we're going to have as our guidelines to being able to kind of add multiple vectors together. Alright, so first of all we're going to kind of go through the definitions of what vectors and scalars are. This should be repetitive as we went through this in chapter 2. So if you want to write these down, you certainly can. It's not necessary, but I would highly recommend it. That way it's, somewhere in the vicinity of what you're looking at for your notes in chapter 3. Okay, so first of all, we know a scalar quantity. We talked about it before, that it has magnitude and no direction. And so I mentioned that you guys are scalars in terms of physics because you guys have no direction just yet. Some of you are starting to get some direction. I noticed the other day you guys are doing really well with the graphing and also kind of picking up on some of those kinematic equations. And so remember that that information is going to be vital to the rest of the course because we're going to be looking at graphs, we're going to interpret graphs, but we're also going to have to use a lot of those kinematic equations because they're kind of the foundation of a lot of Newtonian physics. Alright, so examples of scalars, some of the quantities that we talked about before would be distance. We can look at speed. I gave you a couple other ones on there. So volume and area, time, mass, that might be it. Yeah, that's it. Okay, so when we're looking at each of these, the ones that we've already kind of covered in this class would be looking at distance here. So we kind of covered distance. We know what distance is. It's a measurable quantity in terms of meters. And then we can look at speed. Speed is also measured in standard SI units of meters per second. Same thing with volume and area are directly based off of those. Remember, area would be meters squared, whereas volume would be meters cubed. Time measured in seconds, and mass, once again, in kilograms. Now these are all scalar quantities, meaning that they don't require a direction. Like if I said, I want to know the volume of your water bottle, then I would be able to either look at the label and it's going to tell me a number, but it's not going to be like, your water bottle is 16.9 fluid ounces west. Doesn't make sense because what we're looking at is just a measurable quantity, and so that's once again just a reminder what scalars are. So scalars do not require a direction, so that's the key, no direction. Okay, and so as we're looking at each of these quantities, you want to recognize that all of them are going to have units that are once again in the SI system. Now naturally we can have units outside the SI system. These are ones that I would give you guys, but specifically keep them in this system. Alright, so that brings us to vectors then. If scalars have a magnitude but no direction, then that means that vectors have both magnitude and a direction, which means these are the ones that it matters where you're going, what direction you're traveling. So for example, the distance or the difference between distance and displacement is that displacement has a direction, but then also the displacement, remember, is that straight line distance from start to finish. And so examples of quantities that we would have for these would be, once again, looking at, first of all, we could say displacement, like I was mentioning, velocity, acceleration, force, and that's it. Okay, so as we're looking at displacement, velocity, acceleration, force, these would all require a direction. So as I'm looking at displacement, remember, I would read something as like, if I looked at, say, this road sign here, I can see that that would probably looks foreign, so this would be 22 kilometers, and we would say in this case, let's call it west, just because of the direction it's traveling. So by having this magnitude right here, this 22 kilometers, that is my magnitude of the distance, and or displacement in this case, and west would be that direction. And so we know that we have to have a direction. It could be up, down, left, right, could be positive, negative, could be a cardinal direction. And so we're going to talk a lot more about using those cardinal directions that we mentioned last chapter. Velocity, once again, remember, this is speed and direction. Acceleration could be positive or negative. And forces, which is what we're going to talk about in chapter 5, so you can see Daffy Duck here is applying a force to the box here, and so I would know that that force is traveling in this, say, negative x direction, and we would be able to define its direction then. Alright, when we're talking about vectors, we're actually going to draw them as a specific shape, and that shape is an arrow. And so if I'm looking at this picture, I can see that this is, once again, probably not going to be to scale, because 1 centimeter to me here, depending, well, I guess if I was looking at centimeters on my computer screen, I can see that it actually kind of matches up roughly. That a centimeter on here is going to be 4 meters, so therefore there's about, it's not exact, but it's pretty close, that we could say that it should be about 5 centimeter length on here. It looks a little bit less, more like 4, so it's pretty close. But when we're talking about vector diagrams, you're going to notice that it kind of looks like a ray. And so you guys have seen rays in class, like geometry. But this is not exactly like a ray, because a ray has a defined starting point, but then it continues on and on and on. What this actually does is it's just going to halt. So the length of that vector is really important. It's crucial. So when we're looking at vectors, vectors are going to use an arrow like shown there. The length of the arrow, and this was I was kind of getting to a little bit, so the length of the arrow is going to represent the magnitude. So that is key. So make sure you get this one down in your notes, that the length is going to be the magnitude. So if this length is 20 meters, if I was to draw another vector that has a length of, or a distance of 10 meters, different direction perhaps, then I know that I'm going to be about half of that vector. And so I could say that this one could be a distance of 10 meters. That makes sense? So the magnitude, or the length there, is going to be representative for these vectors, and this is what you're actually going to be doing in your lab later on in this chapter. You're going to have to draw these vectors to scale, and so whenever we go through the lab, I'll explain how to do it. It's very easy. All you got to do is just be really careful and make sure you know how to use a protractor. So for those who don't know how, I'll run through that with you guys, and it should be no problem at all. Naturally, you're going to have some issues here and there. You just got to be really careful with your cardinal directions. Alright, lastly, vector diagrams also require, once again, the direction, and in this case, it's going to be an angle. A lot of times the angles, you can see that this angle here is 30 degrees. It's made with respect to, we could say, this north axis here. Wow, that wasn't north. There, that's better. A little bit of a glitch. And so as I'm looking at this axis, I would say then that I first went north, and then I went west of north. So that kind of clues me in to say that, alright, this is 30 degrees west of north. So if I was to label this vector, I would say this vector is, let's see if we're having some fun issues going on here. Alright. See if I write a little slower. So we're being geometric in our writing now. Okay. So basically that would be written as 20 meters at, this is really fun. So 20 meters at, for lack of time or for not wasting your time, 20 meters at 30 degrees, and it would be west of north, because once again you first go north and then you'd go west of north. So that would create your direction. Alright, so when we're looking at vectors in one dimension, this is something that we kind of covered last chapter, where if I, say, traveled 5 meters and then I wanted to travel another 7 meters, then I would be traveling a total of 12 meters, and that could be my distance. However, what we're also going to look at is the displacement. So remember, all this stuff on this slide is more just repetition of everything we've already kind of covered. So just a reminder, of what the definition of a vector is. So a vector is a quantity which is completely specified by magnitude and direction. They are represented by an arrow, the length being the magnitude, and the arrowhead points in the direction that you're traveling. So if I was to look at the vector at the bottom here, I can see that this vector at the bottom represents positive 10 meters, because I could say going towards the right here would be positive and going towards the left here would be a negative. All right. So if I'm to add vectors in one dimension, this is where it's going to get, a little more difficult, but I think you guys can manage, because if they are along the same plane, all you're going to have to do is just add and subtract them. So for example, if I had 10 meters pointing to the right and 7 meters pointing to the right, then what would be the total resultant vector? Come on, guys, you know what this is, right? Anyone shouting it out? Good. Yep, exactly. So the resultant is 17 meters. Excellent. And so I could actually, if I wanted to, I could kind of piece these together and draw them, where I would have had my 10 meters about right there. And what we're going to talk about is we would actually draw the next one directly from the tip of the last one. And so it's a certain method. You're going to want to jot this down. It's going to come up multiple times, but this is called adding vectors tip to tail. And so what happens when you're adding vectors tip to tail, you're going to take, for example, you can see the tip of this arrow, and you're going to attach it to the tail of this arrow. So you're always going to draw one, and then from the end of that you're going to connect the next one, from the end of that you connect the next one, from the end of that you connect the next one, and you keep on going. And so once you draw tip to tail, then your resultant will go from start to finish. So you'll notice that I started with this vector right here, and I ultimately ended with my last vector all the way out here, so I would draw my displacement from start to finish. And in these cases where it's just one dimension, it's easy to just simply add these two numbers together. However, if I change things up, and this time I have a negative vector, so I have my 10 meter vector. I can see that I have 10 meters going positively to the right, but then I also have a negative 4 meters going to the left. So if I was to draw in my negative 4 meters, something like that. So let's say that's my negative 4 meters. Then remember, my resultant is going to go from start, which is I started all the way at the 10 meter mark, and I'm going to finish at where the negative 4 meter left off. And so this red line, this would be my resultant, and this is a symbol that you will see a lot for resultant. You'll notice that I put an absolute value symbol around the R, and that signifies that my resultant is just going to be a magnitude. So this is a positive magnitude, which means that as I'm looking at that, I know that it just is a measurable value, but I mean, since that's the magnitude, I would also require the direction, which would be where that arrowhead points. So it always goes from start to finish. So in this case, I would say that my total resultant would be, yep, exactly right, guys, 6 meters. Good job. So give yourselves a little pat on the back for that. I know, it's an overbearing task to add and subtract integers, but we can definitely do it. So this is kind of like the extent of what we're going to do today. We're just going real low key, getting you guys just prepped and ready so that you can kind of get an idea as to how we're actually going to start adding vectors. And that'll be some of the last stuff that we're going to get to in this lesson. Okay, so this is ultimately what you guys are going to be doing. So I'm going to leave you guys a little bit of time here to write this down. So I won't be talking. Probably just like a minute or so, because then naturally you guys can pause it when you need to. So actually instead I'll just go ahead and pause this, and then when everybody's ready, just make sure you let whoever's kind of controlling the computer to go ahead and unpause for you guys. Alright, hopefully at this point everybody has a chance to get down all the different steps. You'll notice that I added these steps. They might come in different form or different manner. I think actually I only did 4 or 5 steps. I think I did 5 steps in one of the examples that we're going to do on the third lesson on adding vectors. Alright, so here's the process. Ultimately what we're looking at here is we're first going to draw our vectors on an XY axis, and that's just your standard graph. So If I was looking at an XY axis, you just want to make sure, oops, that's not good. There we go. You want to make sure that you do put your X on the X-axis, which would be the horizontal, and your Y on the vertical axis, so not like what I did. Alright, showing them attached tip to tail. So if I was to draw two vectors, then that's kind of what I'm going to see. So let's say I have a vector and it points this direction. In this direction we're going to make positive. We'll say it's just a value of 5 meters. But then I have another vector, and let's say this other vector points, it's got an angle in it. We're not going to do the math today, but just kind of go through the steps and the motions a little bit here. So let's say this angle is 40 degrees and the hypotenuse is 4 meters. So if I had these two vectors and I want to add them together, this first step says to draw them. Now I can show them attached tip to tails. For some of you, it might work well in that you can visually see it. And for one of the other methods that we're going to do later, you will need to draw them tip to tail together, and you'll see what I mean. But if it helps, like I have in the parentheses here, draw them separate. And so you can see I kind of have both of these separate here. So my 5 meters, if I was looking at it, then my second step here says I'm going to calculate the x and y components of vector 1 and vector 2, and so on and so on. And so you can see in parentheses here, you're going to be using sine and cosine. So that's where those trig functions are going to come in that we're going to talk about a little bit later today. Okay, and so then I would look at this first vector and I would say, okay, with that first vector, do I have any angle to it? And if I do, then I'm probably going to have a number for both the x and the y, kind of like in this one. So there would be my x and there would be my y for that second vector. However, if I don't have an angle, like I see this one's just completely horizontal, then one of the x or the y's is probably just going to be 0. And you'll see whenever we start going through some example problems. Okay, so that's what you're going to do in the second part, is you're going to find these x and y components for both your vectors. Then in the third step, you're going to be adding the x's and adding the y's, and in doing so you're going to end up with this big total x and this big total y. So whatever this whatever the x component is for that first vector, and then the x component of the second vector, I would add them together, and that's going to give me this total x in the third step. And then same thing, I'm going to find whatever the y component is for that first vector, find the y component of the second vector, add them together, and that gives me the total y for the third step. The fourth step is simply just to kind of draw a new triangle. Be careful and make sure that you do use this tip to tail method, because otherwise you're going to get the wrong direction. Okay, now you can start by drawing your x or your y, it does not matter. So if I was to say, in this case it looks like it's going to be a positive x and a positive x, so I would basically be drawing my x first, and I would have, like you notice, that it's going to be 5 meters plus whatever's here, which is going to give me a total x. And then my total y, this one actually doesn't have a y, and this one has a y going up, so then my y is just going to match what I would have in my second vector. So then my resultant, remember, goes from the start of everything all the way to the finish, and that would be your resultant again. Okay, so that's kind of what you're doing for this next one. You're going to draw them tip to tail. Notice that you're always going to get a 90-degree angle because you're doing an x and a y, and x and y are always perpendicular to each other. Step 5, then, what's going to happen is you're going to be adding the resultant's x and y values, or in other words, this is a right triangle, and to solve a right triangle we can use Pythagorean theorem to find that guy right there, that resultant. Okay, last step then, and this is going to be tricky for some of you. We're going to use our total x and total y components. It's a lot easier just to use, so that's the y, that's the x. It's a lot easier to use these two components, and we're going to use the tangent function, except we're actually going to use the inverse tangent function. And we'll talk about what that means too. So when you're looking at all these steps, like, it's going to kind of come second nature, but ultimately what's happening is you're going to have two vectors. You're going to break them all apart and make an x and a y component out of each. Then you're going to combine them all back together. Total the x, total the y. With that total, you're going to form a brand new triangle so that it's going to include all of them, and then you're just going to solve this triangle like you have probably done in some sort of math class, solving a triangle, finding different sides. So that's kind of what you're doing there. Okay, So now let's get tricky with it. When we're looking at trigonometric identities, first of all, we want to talk about, no, well, write them all down first, and then we'll talk about the main ones that we're going to be using. So when we're looking at trigonometric identities, those are things like, as you saw on the previous or on the next slide. So like sine theta, and theta is once again just a symbol for the variable or the angle. We can actually just use an x, we could use an a b, it doesn't matter what you do. Sometimes you might see me using beta, so I use a lot of Greek letters when I'm using my angles, but usually it's theta. Okay. Then you also have cosine theta, and then you have tangent theta, and then the kind of opposite, or the more or less not the inverse, but basically flipping it, so the reciprocal of sine would be, anybody? Bueller. That would be cosecant of theta. And these are like basically the ones on the left side are the ones you're going to want to know. The ones on the right side we're not going to cover. You won't need them for this course. Okay. Going along with cosecant, you're going to see that it's going to be secant theta, and you might learn these later on. And then with tangent, you have cotangent. Okay. So when you're looking at all of these, they come in a very nifty way of remembering, and we're going to talk about that one tomorrow more specifically, because that's where we're going to use a lot of those more and kind of jump right into breaking down all of our triangles into different components. Alright, so like I was mentioning on the next slide, these are the ones that we're going to be focusing on for this course. And if I'm looking at sine theta, well, we're going to add in, and like I said, we're going to do this a little bit later tomorrow, but the sine of theta is going to be found by doing the opposite over, that's bad, opposite over the hypotenuse. And we'll just fix that a little bit. Lovely. Okay. So opposite over hypotenuse. And then cosine is going to be the adjacent over the hypotenuse. And we'll talk about what these words mean, because some of you are probably like, I have no idea what he is talking about. If that's you, go ahead and raise your hand. Some of you probably didn't raise your hands, but you definitely haven't seen this before. You're a little bit confused. It's what always happens. If you are confused, though, and you do have questions a little bit later, some of these are going to be answered tomorrow, like I mentioned, but by all means, please email me. All right, and tangent theta is going to be opposite over adjacent. And as I'm looking at these are all going to be based off of a right triangle. So all of your trig identities always have to be a right triangle. So if I had a right triangle right here, that's the best I can do with right triangle. Not too bad. And we'll go ahead and connect it even though it had a line. Okay, so ultimately these are all going to be based off of this value or this angle of theta. So it depends where you actually place it. So if I put theta down here, then that means that the sides are going to be based off of where I chose theta to be. So this side right here is the one that is right next to the angle. And so out of all three of these words, this opposite, adjacent, and hypotenuse, which one means next to? Excellent. So it's the adjacent side. So if you wanted to, on your triangles, you can always label them. It's no big deal. So label it with a capital A for adjacent or a lowercase a. I usually use capital letters when I'm doing these just so it doesn't get confusing in case you have like some smaller letters later on, like acceleration is a lowercase a. So that usually helps to keep it capitalized then. All right, and so then if I'm looking at this angle, then I know that the side that is directly across from the angle would be opposite of that angle, theta, so that's my opposite side. Which leaves then the angle that is across from the 90 degree, which is the largest of the three angles here, that would be considered your hypotenuse. So your hypotenuse will always be across from your 90 degree angle. The adjacent side is always once going to be the one that helps create this angle with the hypotenuse. And then the opposite side is going to be the one that you find across from theta. Now naturally, if I was to have the same exact triangle, not exactly the same because I can see it's a little stunted, but this time I made this angle theta, then what would happen is this is my opposite side, This is my adjacent side, and my hypotenuse hasn't changed. So you'll notice the hypotenuse doesn't change, but where I place the angle is going to be really crucial. And when you're doing these vectors, remember, let's say the vector, I was starting here and I was drawing the vector this direction. That means first, if I'm kind of following the outside course, I'd be traveling along the eastward direction, and then I'd be going northward, and so I would be adding my vectors tip to tail, or adding the components tip to tail, so x and then y. And that's what would include that angle theta. With this one, however, I'd be going south, and then I'd be going west, which is a completely different angle measurement in terms of my cardinal directions. So not angle measurement, but different cardinal direction, which tells me that these two triangles wouldn't be exactly the same because the direction would be completely different. This hypotenuse might be exactly the same, but the direction is, this one would be north of east and this one would be west of south. So they're completely different. Alright, so as I'm looking at these, this is all you need to know for right now, just that sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And we're going to talk more about these as we kind of go through these lessons. I just want to briefly mention each part and kind of break them down slowly for you. So if I was to test it with the triangle, and I'm just going to throw some numbers on here for you guys. So let's say this hypotenuse is 13, let's make this 5, and let's make this 12, okay? So what I want to do is I want you guys to find the sine of, let's label some of these angles. We'll label this angle B, and we'll label this angle A. That way, you know, it's easier for you guys. So let's say if I wanted to know the sine of A, then that means, remember, A is, good, opposite over hypotenuse. So then if I'm looking at angle A, I know that the opposite side would be the 5, and the hypotenuse is 13. So that would just be 5/13. And so that's kind of like one way just to get you familiar and comfortable with doing all the sines and cosines. Okay, and let's say I did cosine of B. I'm going to show you something cool with this one. So cosine of B, go ahead. Cosine is adjacent over hypotenuse. All right, so the adjacent side is, interesting. And the opposite side is, also interesting. So cosine of B comes out to 5/13. Interesting. So in a triangle, if I'm looking at A and B, the sine of one angle is equal to the cosine of the other angle. That's pretty nifty. Something important to know. And if I, once again, let's try tangent. So let's do tangent of, we'll do tangent of B. So if I did tangent of B, remember tangent is, exactly, opposite over adjacent. If you didn't say it, I know that you're thinking it. Or you look down at your notes and you found it there. If you need help, I put these on the front of your best friend, so you can find those in the front middle section of your best friend. Alright, so it's opposite over adjacent. For B, the opposite side would be the 12, so I would write this as 12. Ooh, that's not a 12. There's a better 12. Getting geometric again. So 12 over the adjacent side, which is 5. So this is an improper fraction this time. Okay, that's a terrible 2. That's better. Okay, so 12 over 5. And so if I'm kind of just using these trig identities, it just helps to kind of go through each and every single one of these. All right, let's try another one. In these, you'll notice I'm kind of giving you triangles that should look pretty similar to something you may have seen before. So let's say this one, I put some two lines between those, and this is a 90-degree angle. That's what type of triangle? Oh yeah, isosceles triangle. And specifically, if these are the same, then I know that these angles are the same as well. And these are called your base angles. So if this is 90, then I can add up the total angles inside a triangle to be 180 degrees. So 90 taken away from 180 gives me 90 remaining, and then I split it in two. So this is a 45, 90 triangle. And these have special relationships. You guys would know these for the SAT as well. And they always have them on the front page of your SATs if you're taking those. All right, so if I was using this, there are actually some nifty little things to know and that would help you, so that way you don't have to do a ton of math. You'll find out later whenever I'm kind of going through stuff in class, and we'll have like an angle sine of 30. So immediately I know that the sine of 30 is 0.5, or the sine of 45 would be like 0.707. And so it's helpful just to kind of have these all memorized, but I'll kind of give you a way on the next slide to help to remember them. So if I had this one and I said that this is, I don't know, 12 and 12, and I don't know, say this would be, I'll do a real quick calculation so that I am accurate with you guys. Let's see, 12. Okay, so it'd be about 16.97. I was going to say about 17. I just want to make sure that I wasn't going to be over. All right, so about 17. And so if I used whole numbers there, then if I was saying that I wanted to know what the sine of 45 is, notice that there's two 45, so it really wouldn't matter which one you chose. And sine of 45 means it's going to be opposite over hypotenuse, which would be 12 over 17. And if I did cosine of 45, what do you notice happens? You're right, it doesn't matter. If I'm doing the adjacent over hypotenuse or opposite over hypotenuse, it ends up being the same thing. So sine of 45 and cosine of 45 are always going to be 12 over 17. They're always equal to each other. And so that's something to know whenever you have a 45-degree angle. Your sine and cosine will always be the same value. So it saves you some time. All right. So last thing then, for those of you who have learned the unit circle, awesome. If you've ever needed help with those, I know that a lot of times teachers will be like, all right, you got to memorize all these different angles. And so there's angles, there's like a 30-degree angle, and you got your 45-degree angle, which would be the one from there all the way to there. And then you got your 60-degree angles in here and 90, so any increment of basically 30s or 45s. And so there's a nifty, neat way to remember a lot of these. First of all, you probably have seen this before. I'm going to put an A here, I'm going to put an S here, I'm going to put a C over here, and I'm going to put a T over there. And so what these stand for are going to be your trig functions, sine, tangent, cosine, and this is all. And so this tells you where all the different trig functions are going to be positive or negative. Specifically, if it is in there, it's positive, so all of them are positive here in quadrant 1. Hopefully you remember your quadrants. Quadrant 2, quadrant 3, and quadrant 4. Okay, so that means that sine is positive in the top two quadrants because sine typically deals with the y, and so these are positive y's. Cosine deals with x a lot more, or it's kind of like symbolic with x, so it's going to be positive in both of the ones on the right hand side, which is where you have your x-axis being positive. Tangent is going to be positive in these catty corner ones, so in the all section, and then also down here in quadrant 3, which means that it would be negative in quadrants 2 and 4. So that's helpful to know because then that kind of already clues you in as to where your angles could be located. But the tips and the tricks I'm going to give you, so if I was, say, finding the cosine of an angle, theta, then I know that if I'm finding cosine of angle theta, I'm going to set some fun stuff up for you guys. And you guys are going to be like, oh my gosh, what is this? And all I'm going to do is I'm going to place this over 2. And so if I asked you guys, what is the cosine of 0 degrees? And if some of you had to type it in, by all means go ahead and type it in. But the cosine of 0 degrees is 1, exactly. So why'd I write a 4 there? Well, what's the square root of 4? Nice, 2. And what's 2 divided by 2? 1. Nice. All right, so if I am looking at 0 degrees, then I know that the cosine of 0 degrees is going to be the square root of 4 over 2, which is 1. All right, let's do all the special angles then. So we're going to do 30 degrees, we're going to do 45 degrees, we're going to do 60 degrees, not L0 degrees, and we're going to do Oh man, this is terrible. The pen's acting up again. And then we're going to do 90 degrees. Okay. So if I have a 4 here, then I'm going to start counting down. And I'm going to place a 3, and then a 2, and then a 1, and then a 0. So if I took the square root of 3, what's the square root of 3? Square root of 3. Can't do anything with it. But then the square root of 3 over 2 is the cosine of 30. Cool, huh? Let's check the next one. So the square root of 2 over 2 is the cosine of 45. So if you were to type that in your calculator, cosine of 45 degrees, as long as you're in degree mode, you want to make sure that your calculator is in degree mode for this class, because otherwise you're not going to get the right answers. So before tests and such, I will constantly try and remind you, make sure you're in degree mode. To switch your mode, on the TI calculators, there is a little section labeled mode. It's one of the top buttons underneath the screen. If you press that and you go down, you'll see that either degree or radian will be highlighted. You want to make sure that degree is highlighted and not radian. To get out of that, you can basically quit. So you can exit out, or on the TI-86s, my calculators, you got to hit like second quit to get out of there, and it'll kind of clear you back out, or second mode, or whatever it is. Alright, so let's continue with these. So if I had 60 degrees, if I take the square root of 1, square root of 1 is 1, and 1 divided by 2 is a half. So the cosine of 60 degrees is a half, and the last one, square root of 0 is 0, over 2 is 0, cosine of 90 degrees is 0. And you could do the same thing with sine. This is going to be all fun. Okay, so sine theta, that's a theta, going to be basically the same angle, so I'm not going to rewrite those angles since this is acting up again on the screen. And so this time, instead of going 4, 3, 2, 1, 0, I'm going to go 0, 1, 2. That's a great 2. There it goes up. That's like a E3. That's better. 2, 3, and 4. And so as I'm looking at these, I know that the sine of 0 degrees is going to be the square root of 0 over 2, which is going to be 0. And naturally, if I'm all the way out here, then the sine is not going to be, it's non-existent. It's 0. There is no sine value. And this is kind of with your unit circle what those ordered pairs would be. So the x is usually the cosine and the y is the sine at that point. So if this helps you, excellent, and then you can kind of use it for whatever purposes. If it helps you with this class, that's great. You're probably not going to use it a whole lot, so you won't necessarily need it entirely. All you're going to be using is the cosine and the sine and understanding how to use those. Alright, so that's your first lesson in terms of looking at trig identities and how to add and subtract vectors in one dimension. And so what you're going to look at tomorrow is going to be the trig behind it. We're going to kind of talk about that a little bit more. All right, all done.